So first of all, I have a sin to confess. I spent many years in the UK, and it was for me a point of interest to go and know all places possible in Great Britain. And I've been almost everywhere, but there is two places that I haven't been in the UK that are fairly known. One is Aberdeen and the other is Brighton, I have to say. It's one of the very few places that I didn't have the pleasure to go. Well, this is a way of being around. I've heard many good things, that it's a great place, but unfortunately I don't have the pleasure to know the place. Maybe one day. So I'm going to talk about accelerating Python processing with GPU computing. I had unfortunately a computer crash like 2 hours ago, and I had almost to redo the presentation, but I think I have everything that I want to talk about. So this is not an introductory presentation. I know that this might not be asked to the organization, but if somebody feels completely lost, or if I go too fast, please just write something on the commentary, because this can very easily be I might go too fast because I have to condense a lot of material. Okay. So I'm going to talk about accelerating Python processing with GPU computing, and before that I have to introduce a few other concepts. Here. So a bit to start a little bit about me. I started in CS, did a master's in bioinformatics. Then I wanted to work with poverty diseases. So I ended up in Liverpool doing a PhD in infectious diseases, which currently it's a topic that it's on everybody's mind. I work in malaria, not in coronaviruses, but it's a field that I'm quite conversant with it. Then I did a postdoc career still in the UK, but I was mostly programming Python pipelines to process bioinformatics data. I'm currently a data engineer in the biotech space. I've been using Python for 15 years, like as a first language, but for 24 years, and I've contributed to several open source projects. You can find that on GitHub. I have 2 books currently. I'm writing Fast Python for Data Science, and I have a couple of bioinformatics books, and there's going to be a 3rd edition soon of the bioinformatics one, and the Fast Python one is I'm currently finalizing writing it. It's already available, the first few chapters online. Okay, the presentation. I'm going to I want to talk about making the code more efficient with GPUs. But to get there, I have to go through a few things. One is that Python is slow. And I want to spend a little bit on that. And then I want to give you an overview of the alternatives that you have, because there are many alternatives before you consider going into GPU computing. Then I'll talk a little bit about GPU processing. A very brief overview. It's a complex topic. That being said, don't run away from it. Lots of people run away from it. It's complex, but it's doable. Then I'll talk about the Python ecosystem for GPUs. Then I'll talk a little bit about Numba, which is an accelerator of Python code. And then I'll talk a bit about GPU computing via Numba. I'm assuming that you have a vague idea about NumPy. I'll have a few examples of code with NumPy, but they are not. I do assume that people who have at least some exposure to the data analysis stack, NumPy, SciPy, Matplotlib, all that stuff. So I want to start about the issue that Python is slow, and there are two sides of this equation that I would like to talk about. One of the sides of the equation, which we will deal with at the end of the presentation, is that Python is a dynamic language. And so it's not fair to ask a language with all the dynamic dispatching that Python has to be as fast as a language like C, simply because the infrastructure of dynamic languages requires some overhead. So it is to be expected a degree of slowness. That being said, the C Python interpreter is horribly slow. And actually, Guido van Roosem in May, he was supposed to go. I don't know if you went through, but I think he was supposed to go to Microsoft, and he could choose his own project work for his team. And what he wants to do is to make the Python interpreter, the standard Python interpreter, twice as fast. And that suggests that the implementation itself has performance problems. And if you look at stuff like apparently as simple as how a sum is done by the interpreter, the code is completely crazy. For several reasons, but one, it's because of all the dynamic dispatching features. And another is it's that because of code evolution in the last 30 years, there is lots of stuff there that slow things quite a bit. So Python is slow, and is slow for these two reasons. It's a dynamic language, so it's fair to be slow, but the most used Python interpreter is problematic. Okay, there is no other way to put it. So how can you speed up Python? One alternative that's not here is that you can try to use another interpreter, but I'll not go there. But you can write better code, and it's kind of incredible when you look at some code that simple things that people sometimes do with their code that could be substantially optimized. The one that immediately comes to mind is search in lists, which when you have to search an element, you have to go through the whole list. So it's the complexity is with the size of the list. But if you can, instead of using a list, you can use a set, because a set is based in a dictionary, then the complexity is log n. So this is one example, if you can, because sometimes you need a list, of course. But there are gazillions of examples. I'm not going there, but it's an avenue, and I would start there, and I would use profiling tools to do that. The other one is concurrency parallelism. Of course, some of you might have heard of the global interpreter locks, so you can actually not do your multiple threads in Python will run serially, so they will not run in parallel. You'll have to use multiprocessing with Python, and then you can actually make use of more than one core. The real way people actually optimize 99% of their code is by using libraries. So a library like NumPy, it's written, most of the inner loops are written in C or Fortran. So when you call NumPy, there is a stack there, and not only C or Fortran, but it uses libraries like WAS that are normally very optimized to the hardware. So most of the time, and actually our preferred way to optimize this is by using libraries that somebody else did for us, NumPys, Pandas, etc. The other is by using lower level programming. So that means using, writing a part of your code in C or in Rust, or using Cython or Numba. And Cython and Numba, so Cython compiles your codes into C. Numba is a just-in-time compiler. I'll get there in a minute. Another is to use a network computer, that is to use a cluster, or to use the clouds. And you might have heard of things like Dask or Spark. And then there are architecture issues. And there is actually a lot to be said about writing code that optimizes for CPU, but I'll not go there. There are also issues with storage, which I won't go there. And here I'll talk mostly about GPUs. But there is a complete other layer on top of these of alternatives to using GPUs. Okay. So one of the things that complicates people using GPUs is the fact that the processing model is completely different from what you're using. Remember that GPUs were made originally, and one of their biggest uses is still, GPU means graphic processing units. So the idea is to process pixels, which means that the GPUs, the architecture, have thousands of small compute units that are very simple, that each one individually is actually not very fast, and they are supposed to be doing similar work. Essentially, the paradigmatic code is pixels on the screen, and they are and the operations that are done on each pixel are more or less similar. But there are many units, and they tend to be slow, and so they are not amenable to sequential programming, which means a completely different paradigm in terms of thinking. So when we talk about pixels on the screen, we can also talk about elements in a matrix. And when you start talking about elements in a matrix, then we enter all the stuff regarding data science and modern algorithms, because almost everything at the end of the day is based on a matrix. So because you can process matrices with GPUs very, very efficiently, then many of these problems can be treated, can be easily processed by GPUs. GPUs, if your code is sequential in nature, you don't want to use a GPU, okay? So this is an example that lots of people give an analogy to understand the difference between a CPU and a GPU. This is not my creation, but you see this in other slides. A CPU is a bit like a motorbike. So it's really a fast motorbike. So it's really, really fast. If you want to move a person or two, in the sense that you have multiple cores currently in modern CPUs, the fastest way to move a person or two is by using a motorbike or a fast car. But if you want to move, you need to move 50 people, there is no way a motorbike is going to compete with a bus. And you put lots of people inside the bus, and you move them at probably a third of the speed than a motorbike. But in terms of as a bulk operation, it's substantially faster. Okay, I actually don't have here slides about how faster things can be, but if you have operations that are parallel in nature, you can easily get 2 to 3 orders of magnitude increases in speed. Sorry, I have a couple of slides that are still in drawing form, and I'm, as you can see, I'm no Picasso. And this is the internal architecture of a GPU. And the fundamental point here, I don't want to spend a lot of time with the details, is that you have a hierarchical architecture. So you have what people tend to call what people tend to call as CUDA cores, which is a terminology from NVIDIA, and but those cores are itself inside of what's normally called a streaming multiprocessor, and then the GPU is a collection of streaming multiprocessors. And the reason why this is important, though we are not going there, it's because of cache memory. So as you see, transferring stuff from memory around is actually where we spend a lot of time. And what happens with GPUs is that they have a GPU memory, which is normally what you see in say a GPU card. It has 6 gigabytes of whatever. It has a shared L2 cache, and then every every streaming multiprocessor has an internal L1 cache that is shared with all the CUDA cores. Okay. A word about terminology. This can get complicated because you have NVIDIA terminology, AMD terminology, you have OpenCL terminology, and this can get confusing. It's probably when you are starting, it really can get confusing. So one of the important issues, as I said, is transferring of stuff from memory, but there is one that's substantially more important. It is the communication between GPU and CPU, because remember that memory, at least in simple view, the memory from the CPU and GPU are isolated. So that means that you have to transfer whatever you want to do from the CPU to the GPU and sometimes back, especially if you are doing data analysis. This is not the case with graphics processing, which means that the time to do that transfer has to be factored in. And if what you need to do is actually quite small, the price that you pay with the transfer can be more than what you gain by using a GPU. So now I would like to talk a little. So let me interrupt here and just to ask, am I going too fast? Does anybody has any complaint? I can go back and explain things a bit better. I'm going to go a bit into more detail in the next few slides, but if something was not clear, and that might be detrimental to continue an understanding of the presentation. Does anyone have some pressing issues? So if nobody is saying anything, I will assume not, and of course I'm available for questions at the end. So with regards to GPUs and Python, there are a few things that I would like to talk about. First of all, is that unfortunately a good part of this presentation is vendor dependent. Most of general purpose GPU programming happens on NVIDIA cards. There is stuff on AMD, and these are the two vendors that matter. So Intel is not relevant in this space, though you can use it with OpenCL, but it's not relevant in space. So most of what I'm going to present is NVIDIA based. Sometimes you have alternatives on the AMD space, but most of this is NVIDIA based and assumes that you have a recent NVIDIA card, which nowadays, because of chip shortage, they are not easy to find, but you can go back one or two. As long as the architecture is Pascal, you are fine. Of course, if you are on the cloud providers also have GPU machines for you to use. So GPUs and Python. There are two ways you can go around this. One, the easy way is you don't program anything. You just use libraries that take care of that for you. The only thing you bring to the table is a GPU. And then there are plenty of libraries that you can more or less replace seamlessly compared with CPU versions of libraries. So for instance, where you have BLAS, there is cuBLAS. Where you have NumPy, there is cuPy. Where you have pandas, you have cuDF. For scikit-learn, you have SQML. And then you have other interesting stuff like Blazing SQL, which if you have a CPU, allows you to write SQL code to access, say, data frames and CSV files. And so one solution, if you have a GPU, is then just to consider using pre-made libraries, okay? And I'm going to talk a little bit about that. The other alternative is for you to do some lower level programming. And this can be, so to solve problems, try in as much as possible to use an existing library. writing low-level programming for GPUs in Python, it's possible and it's fun and it's sometimes mind-bending. And I want to talk about the two approaches. There is not, so I'm going to talk about high-level libraries a little bit, give a simple example, and then go to talk about low-level programming. Okay, and yeah, that's mostly it. So I'm going to give an example with CuPy. So CuPy is the NumPy version for CUDA, for NVIDIA GPUs. And on top, you have here a very, very, very simple example of an operation, which essentially takes a matrix of a matrix of size 5,000 times 5,000 of ones of a byte size, and then does a multiplication. Simple, right? You can simply drop in. You can replace NumPy by CuPy, and the code is exactly the same, okay? So this makes your life very, very easy. It's not always like this. There is stuff that's not implemented, or it might have a few differences, but in many, many cases, you can just drop in, replace one library for the other, and you can, in many, many cases, get very, very, very large speedups just by doing this. Probably not in multiplying by 2 because that's not really much to be done, but for more complex things. I want to talk a little bit about making the two libraries talking, because when you have a CuPy example, if you want to send it to, say, a library like Peel to do drawing or to Matplotlib, they don't know how to talk with CuPy, because remember, a CuPy representation is stored on the memory on the GPU, and we need to have a NumPy representation to talk with other libraries. So one of the things that we need to do is to do communication, and take here this example. And so the code is very, very simple. And if you go to this line, you are creating a CuPy matrix. So it's on GPU memory. And if you print the type, it will give you something related to CuPy. If you want a NumPy matrix, you have to do this. And remember, when you do this, you are converting the format, but you are also doing a memory transfer to the PCI bus from the GPU memory to the CPU memory. All this happens in the GPU, so there is no transfer in. In this case, there is only transfer out. Okay, but there is some transferring going here, and this would be a NumPy matrix. If you do this would, everything would happen on the GPU, and if you do this, of course, you are already in NumPy space. Everything will happen on the CPU. Okay, so there is an issue that I want to reiterate the issue of communication, but I also want to discuss a little bit the issue of communication, of memory communication, but the fact that you sometimes need to transfer into the CPU representation to continue. This is particularly important with NumPy and cuDF, because cuDF pandas, because especially NumPy, it's at the bottom of all the data processing stack. And so this tends to be quite simple. You have a drop-in library. It's obviously not totally simple, as I said, but we can work. It's the easiest thing to do. But sometimes you need to code stuff yourself. And this happens both on the CPU and GPU. And for that, you have generally three alternatives. One is to use a low-level language, like C or Rust, or variations of C for the GPU, of course. So that's one of your alternatives. And so you have your Python codes. You use, for example, a profiler, and you find the part that's not efficient, and you rewrite that part, and you link it using Swig or something like that, and you link it. Most of your code is still Python. The inner part is written in C or Rust or something like that. You have two other alternatives. One is called Cython, where you essentially write a Python code. You do some type annotations, and these type annotations are not like the Python modern Python type annotations. They are specific to Cython. And what Cython does, it takes your code, generates a C representation that does all the linkage, but it's actually C. It's Python. You write Python, annotated Python, and it generates you C code, which can be orders of magnitude faster. The other alternative is Numba. And we are going to use Numba here, and Numba, it's normally the easiest of the three. So in terms of complexity, this goes up. Numba is the easiest, then Cython, and then using a low-level language. I don't believe, unless you know C or Rust or something like that, Cython is probably, you don't need to go further than Cython, I would imagine. But with regards to Numba, what you do, you annotate a function. It's very easy. You annotate a function, and what Numba does, it does just-in-time compilation. It works a little bit like the JVM for Java. It takes your code, generates an LVM representation, and compiles it in runtime. So this will happen when your code is running, whereas with Cython, it is compiled before it's run normally. And let me give you a simple example. And for this, I have a function here. Don't think much about what the function does. This is a Mandelbrot function where the input parameter is a complex point, a point in complex space. Think of it as it's a number. Python supports natively complex numbers. And this function essentially computes the Mandelbrot set, which is the image. I should have had the image here, which is a very known image that does a nice graphic. Probably most of you have heard of it. How do you do a Numba version of this? Well, it's quite simple. You from the Numba import JIT, and this is a CPU version. Okay. You do from Numba import JIT, you annotate it, and that's done. Magic, okay? And it's really like this. There are quite a few caveats, as you can imagine. I'm not going to details here, but a function like this will you probably gain 1 or 2 orders of magnitude just by doing something as simple as this. There are a few caveats. I'm not going into the details because I don't have time. So this code is quite easy because you can infer the types quite easily. So these are just integers going around, or complex numbers. So these are very primitive types. But if you have complex types, complex objects, there is sometimes Numba will have to call the Python machinery. And when you call the Python machinery, you are done, okay? So you immediately will hit the global interpreter lock, you enter the Python interpreter. So with complex objects, it's really complicated. It's better if your interface deals only with numeric entities or maybe strings. That's the best. Numba plays well with the NumPy stack. And if you want to dig deep into the problems of Numba, actually, Cython, because Numba, it's magic. So if you need to solve a problem, use Numba. But if you want to understand the details, if you use Cython, the problems that you find with Cython that you have to solve manually with Cython are the same that Numba is hiding from you. So if you actually use Cython, you get an understanding on the problems of Numba, because they are essentially, Numba doesn't expose you the problems, Cython exposes you the problems and allows you to correct for it. So actually learning Cython is a good way to understand Numba's limitations. So how can we do GPU computing with Numba? That's easy, right? So let's think of an example that we don't want to do. And so we are going to multiply an array. So we're going to double an array. And this is the code that we don't want to do. This is sequential, and it's going point by point, okay? And a GPU cannot do anything like this. What a GPU will do is, so you don't call the function a single time. You call the function for every element in the array. So this function here is if you have an array with 1,000 elements, what the GPU will do, or what you want the GPU to do, is to call 1,000 functions. They are all similar, and they will run for a single element. Okay, and how do you know which element to run? You can actually ask CUDA, tell me what's my element. So what you do here is simply ask CUDA, tell me my element on the grid, and with that you just compute a single element, and the whole infrastructure will call this for all we'll call this for all elements in the array. Okay, so we are done, right? Not totally. We still have a problem to solve. And remember this. So Numba once requires you to tell how you want to spread your computation across cores and streaming multiprocessors. So what you do, you have to specify how many threads you want. You have to divide the computation in blocks, and you have to specify how many threads you want per block. And preferably, you want the number, if you have an array of a size of 1,000, you want a number that is the same. If not, your code has to be a little bit more complicated, but I don't have time to delve into that, and it's not very important at a conceptual level. So instead of calling the function double, you call with this slightly uncommon syntax, where you say, I have these threads per block and these blocks per grid. And how do you determine these values? Well, for code that doesn't talk, so when you are doing a double, you don't care about the values around. That's actually not very important, because in terms of performance, this becomes important when you need to hit neighbor elements, and in that case, you want to make sure that they are on the closest cache possible. So you want your blocks to be as close to the closest cache possible. But that is going in way deep into the rabbit hole. And what I just want to note here at this stage is that you need to say to the GPU, I want to split this in this way. And you can you can do 32 threads per block, and normally with that at this level of codes where all elements are independent, you should be fine. That's not a problem. It becomes a problem with more complex algorithms. And essentially, that's it. This is a very broad overview. It's the biggest problem that I find is that people are afraid of thinking in parallel, but actually just a small piece of your code that normally is taking care of a matrix needs to be thought in parallel. And there are plenty of tools, first of all, to completely make it. You don't have to think about the GPU, you just use the library. And if you have to go there, it's actually quite fun to write code for GPUs. And with Python and Numba, you are actually able, you don't need to learn C and the C and CUDA CL and all that stuff. You can just write your code in Python, and maybe later then you might consider going the C route, but you can write lots of your logic in Python to directly program the CPU via Numba. And that's it. I'm a bit afraid that I went too fast about advanced content. We have a few minutes. I can repeat stuff. I can address whatever questions you might have. Just go ahead.
So why are GPUs efficient for data science?
Because most data science problems are matrix-based, right? So when you think about machine learning algorithms, there is normally a matrix being processed there, an array being processed there. And so the lower level implementation tends to be very, very, very parallel. This doesn't apply to all cases, but it applies to a lot of machine learning algorithms. Think, for instance, neural networks, principal components analysis. If you think about them, they tend to be massively parallel in nature. So this works so this works very well with this subset of problems, because there is a matrix there doing the computation for you at the end of the day.
Perfect. Just a little bit of feedback. Yeah, really helpful overview of something I have not looked at in detail before. And I think that's common.
So I just want I just want to say that obviously, so this is an advanced topic, and there is a list of other stuff that you can do before using GPUs, and just using Cython or Numba, it's a good place to start, or using libraries that somebody programmed for you. So this is at the end of the curve, or if you have GPUs available, you can make good use of them. Yes, they are. So precisely because of all this data science and machine learning, they are available as virtual machines in the cloud. They tend to be Tesla models, and they are fairly efficient. Because they implement everything that you need for all these libraries. So yes, they are. I use them personally, actually. So you want to go, I think the best place, give me a second. I think Rapids AI is going, I think, so you can find a list. Probably Rapids AI is the best place to go, and it will give you a list of, so it has QDF, it has notebooks examples. You'll find a few examples there. Yes, you have everything there at the very end, or a good part of them.
Awesome. I think my dog did have a few questions, but I can't understand him, so I apologize for anyone whose eardrums were burst out during that point. Tiago, thank you very much. That was awesome.